So this topic is the Viterbi algorithm under hidden Markov models. So the matching problem is as follows. We're given output sequence. This vector v is equal to v1, v2 until v uppercase t time steps. And our goal is now to find the most probable state sequence that we shall denote as S star, which is argmax of P S given V. So in T time steps, the HMM would have gone through T states, S1, S2, S3 until S of T. And so there are so many different possibilities. Actually, the number of possibilities is number of states to the power of uppercase T. Those are the number of different possibilities. And our goal is to find the most likely or most probable state sequence, which is equal to argmax of Ps given V. And from the laws of probability, that is the same as Ps comma V divided by PV. Conditional probability is joint probability divided by unconditional probability, which is equal to argmax of P S comma V. Why? Because P of V is independent of the S that we are doing the argmax over. And we shall first focus on how to find max of the joint probability before we do the argmax. So instead of finding the conditional probability, since the conditional probability of S given V is the same as, the argmax of the conditional probability is the same as the argmax of the joint probability. So we will find the joint probability instead. So now let's define a variable delta Ti. The arguments are time t, and we'll refer to that time step as the present or current, and up to t minus 1 as the past, from t plus 1 through uppercase T as the future. So this is the current or the present time step, and I is an index of a state. And this is a maximum of probabilities. So what has been specified is the current step should be Si. And this is the past, and we are doing the max operation over the all possible past states. And this joint probability also includes the output symbol sequence until the present. So plus present output symbols. And we'll introduce a simplified notation here like this. And this is MATLAB-like notation. So what I've done is the states S1 through ST minus 1, that's the past, I have compressed it as S1 colon T minus 1. And the present is ST equals SI, and the output sequence is V1 through T. That's past plus present. And so we are maximizing over all possible past states. This slide will make it clearer. We have delta Ti. T is the present time step, and at the present time step, the state is S sub I. So at time step T, we are in state S sub I. And there are so many ways in which the HMM would have reached this state S sub I. It could have gone through at time step 1, it could have begun with 2 and then gone to 3 and then maybe n and then back to 1 and so on until at time step T it reached state S sub I. So how many ways are there? There are n to the power of t minus 1 possible state sequences through which it would have arrived at this state S sub I. And that's what we are doing this maximization over. All possible prior state sequences. And this is then the joint probability of St equals Si and the output sequence V1 through T, which is past up to present. So the red boxes always, not just this slide, but in all slides in this presentation, will be what we are doing the maximization over. We are doing the maximization over all possible past states here. And St is the present state. And the output sequence is V1 through Vt. So this delta Ti is the maximum of the joint probabilities of the observed output sequence, which is V1 through V lowercase t, and state St equals Xi maximized over all possible previous state sequences. Now what's delta 1i? So the time step here is 1. So there's nothing to do the maximization over. There is no past. And so it maximizes over nothing. And what's this delta 1i then? It's the joint probability of, at time step 1, the state being S sub I and the output being V1, which is given to us. And what's the probability of the state at time step 1 being S sub I? And that's simply pi I, the initial state probability. And what's the output probability V1 given the state is S sub I, and that's the emission probability Qi, V1. Hence, delta 1i equals pi I times Q1, V1. Delta uppercase Ti. So uppercase T is the final time step. So suppose eventually the HMM landed up in state Si during time step St, and it generated the output sequence, which is observed, V1 through V uppercase T, and it would have arrived at this final time step S sub I in so many different ways, passing through any possible state sequence, and what we are doing is maximizing over all possible previous state sequences. So this is what we have about delta. By definition, delta Ti is max over S1 through T minus 1 of the probability S1 through T minus 1, St equals Si, V1 through T. And by replacing T with 1, we have nothing here, so we are maximizing over nothing. So delta 1i is pi I initial probability times generating output V1 at time step 1 given state was Si, and that's Qi V1, and simply plugging the value uppercase T in place of lowercase t, we have delta uppercase Ti equals max 1 through uppercase T minus 1 of the state sequence S1 through T minus 1, St equals Si and V. Now I'll take this and I'll do the maximization over St, because there are so many possibilities for St. How many possibilities? We have n states, and at St this I could be any one of those n indexes. And so let's do the maximization over St equals Si now on both sides. So this is what I have. I'm doing the maximization over S sub T now. And so on this side, this is max of over S T of delta uppercase Ti, which is equal to this. Now this is St uppercase T, and this is the entire previous state sequence. And so if we combine this, this is maximization over S of T, this is maximization of S of 1 through T minus 1. So in fact, if we combine these two maximization, this is maximization over the entire state sequence S1 through S uppercase T, which is this bold S here. And what are we maximizing over? This S1 through ST here, and V is the entire output sequence, which is the same as V1 through T. And what we now need is an expression for delta Tj from delta T minus 1i. That is the recursive relationship that we shall now establish. And before we go, let's examine this. Ps comma V is the joint probability of state sequence, the entire state sequence being S and the entire output sequence being V. And in fact, this is what we are trying to maximize over. So let's begin deriving the recursive relationship. Delta T minus 1 I is by definition equal to the following expression. It's the joint probability of the states until time T minus 1, because T minus 1 is the present, and the output symbols V1 through T minus 1. And we maximize over the past states. So we maximize here over S1 through T minus 2. And so this is what we maximize over. I haven't shown ST minus 2 here because it could look too congested, but this is what we are maximizing over. And this is the current state. And this is the set of outputs until the present, past and the present. So this is delta T minus 1i. Now what happens if I multiply the left-hand side and the right-hand side of this expression with the transition probability Pij? So this is probability of all the states and the outputs until time T minus 1, both until T minus 1, maxed over T minus 2, these states, and St minus 1 equals Si, so the last state is Si. Now I'll multiply this with Pij, this transition probability. Then what happens? So here is delta T minus 1i times Pij. I have multiplied delta T minus 1i with the transition probability Pij. And what was delta T minus 1i? It was the state sequence until T minus 1, and T minus 1's state being equal to Si, and maxed over the past states and the output sequence being 1 through T minus 1. When I multiplied delta T minus 1i with Pij, I got this. I had to add this to my condition, St equals Sj, because Pij is the transition probability of jumping to state Sj given the state is Si, and the state at time T minus 1 was indeed equal to Si. And therefore, by multiplying this probability Pij, I have to add St equals Sj. This is the transition probability. And everything here is shown graphically. So the conditional probability now includes St minus 1, St, and the output sequence until Vt minus 1. Only the state has been extended to St, and we are maximizing from S1 through St minus 2. Now what if I add the max operation here for time t minus 1. So now what I had in the past, delta t minus 1I pij, now I will do the maximum operation at this t minus 1 time state, and I was in Si. This Si could have been anything. It could have been S1, it could have been S2, it could have been S3, it could have been Sj, it could have been Sn. So I would have so many different delta t minus 1I pijs for each of these states. I pick the maximum one. And that's equal to this. Now I was maxing over 1 through t minus 2. I have to include t minus 1 state in my maximum. And so delta t minus 1I pij, when maxed over Si, which is at time t minus 1, I get max of S1 through t minus 1 of P1 through t minus 1, St equals Sj, comma, V1 through t minus 1. So we are getting a little closer to delta t because now the max is over state St minus 1. 1 through St minus 1, which would be involved in delta tj, but we are not yet there because the output sequence in the joint probability is until Vt minus 1. So now let's multiply this with both sides actually with the emission probability. The current step is t, and suppose we multiply the current state, which is Sj, the emission probability of V of t given state Sj, what do we get? So here I multiplied both sides with the emission probability. On the left hand side I have Qjvt, which is the emission probability of emitting this output symbol V of t, Vt, given state Sj. And this condition includes state St equals Sj. And so by multiplying this, we have to add this into our condition, the probability of being in, of emitting output Vt. And this is also part of the condition, as is this. We can join them together. So this is now what we have. Max Si delta t minus 1I pij Qjvt equals max of 1 through t minus 1 Ps1 through t minus 1. That's what it's being maxed over. And the current time being St equals Sj, and the output sequence being V1 through present time t. And this is what? This is the definition of delta Tj. So this is what we have, and that's delta Tj. And this is the recursive relationship that we will need. So here is what we have so far. Delta Ti, this is the definition of delta Ti, maxed over previous time step states, current time step being Si, specified by this index, and the output sequence 1 through t. Delta 1i is pi I qi v1, and delta uppercase Ti is probability of state sequence, all the possible state sequences until uppercase T minus 1 being maxed, ST being equal to SI, the probability of the HMM eventually landing up in state SI, and remember it's a joint probability, so, and the output sequence, entire output sequence. And we ultimately need to find this. This is our goal. We need to maximize over all possible state sequences. Given V, what was the most likely state sequence that generated V? That's our goal. And instead of the joint probability, we are looking, instead of the conditional probability Ps given V, we are looking at the joint probability S comma V. And then we found the recursive relationship delta Tj equals max I delta T minus 1I Pij times Qj Vt. I've placed the max within parentheses because what's outside the parenthesis no longer involves the I, index I. Now, what we need is, okay, so what we can compute is max S P S V, which is P of S star V. We can compute the probability of V being generated by the most probable sequence S star. But do we need the probability? We need the argmax. We don't need the max. We need the argmax. We need the S star. So that's our goal. How to find S star. So in an earlier derivation, we had this somewhere in the middle. So delta T minus 1I, I started off with, and then I multiplied it with Pij, and I got this maximum. Now what's delta T minus 1I? Delta T minus 1I is the joint probability of being in state Si at time t minus 1 and emitting symbol V t minus 1. But there are so many different probabilities depending on the path. One could have come through one path to reach this Si, another possible state sequence to reach Si, and so there are so many state sequences. So we max over all the past, so we max over t minus 2 when we are looking at delta t minus 1, and that's, so delta t minus 1I is the probability, the joint probability of St equals Si and Vt minus 1 along the most probable path. Then when we max it over I, this is what we get. Now we're maxing over the entire S1 through St minus 1. However, this max I operation in the left-hand side or the top of the expression is being carried out over I. So what's the most likely previous state I? If the current time step is t now, then what's the most likely previous state at time t minus 1? Okay, that's what we are maximizing over. While doing the maximization, if we also record the argmax, see, it's the same thing here. This is delta t minus 1 I Pij. This is delta t minus 1 Pij. Here you are finding the probability, max probability. And here, if you extract the argmax and record it, here, right here, So you're recording the most likely previous state that the HMM was in before the current time step t. So what was the most likely state at time t minus 1? That's what's entailed in this argmax here, and let's call this a new variable rho tj. Now all the other Greek variables, alpha, beta, gamma, they were probabilities. This is rho, a state. So rho is a variable, but it records a state. So rho tj equals argmax I delta t minus 1 I pij. So rho tj gives you, if you are in state Sj at time t, what was the most likely previous state I? And that's important to know. So we are at this point here. So we have delta ti, the definition, and the boundary conditions, delta 1i and delta uppercase ti are also known, and we have this expression to extract the S star, which is what we want. And we also have this delta tj, which is given by this recursive relationship. And now we have rho tj equals argmax I. The argmax I delta t minus 1 I comma pij, and that's basically equivalent to this. Here you're doing the argmax, and here we're doing the max. That's the only difference between delta tj and rho tj. Of course, we have qj vt here, which we don't need here. Okay, so with this, we are ready to construct the Viterbi algorithm. We begin by initialization. So it's like the forward algorithm. We are going forward. So we begin with the time step 1. Delta ti for each I is pi I qi v1. Pi I and qi v1. We initialize it for all i's. And so for I equals 1 to n, delta I is pi I qi v1. Now in step t, we applied the recursive rule. So in step t, we assume that we know the probabilities, the deltas for t minus 1, and then we apply the recursive rule to obtain the deltas for time t. So this is the expression that we're going to use. Delta tj is max delta t minus 1 I pij qj vt, and that's this vt. And delta rho tj, remember, while we're doing delta tj, we'll have to find rho tj, which is the argmax of delta t minus 1 I pij. And this is the most probable previous state at t minus 1. So this is the main algorithm. For t equals 2 to n, because for t equals 1, we already computed the deltas. And for t equals 2, and to t, what we do is for each state, we find rho and delta. Now, why wouldn't we have rho here? Because rho is meaningless when we are in the time state. What's the previous state? There is no previous state from here. So rho needs to be computed from here. rho tj equals argmax I delta t minus 1 I pij, and delta tj is max I delta t minus 1 pij qj vt. So we've looked at delta tj using this expression here in one of the prior slides. What exactly is it? Once again, so delta tj here is a joint probability consisting of three components, three events. One is the most likely previous path until t minus 1. The most likely state sequence until t minus 1, and the probability of being in state Sj at time step t and emitting the entire output sequence until v of t. So that's what's delta tj. Now, suppose, of course, I have delta tj at the last step of the Viterbi algorithm. This is what I would have. I would have delta tj for each of these states 1 through n. And what if I take the max of all those delta tj's? What I would be doing is, in fact, extracting S star at time t, because each of these delta tj's is already maximized over the previous history, the state sequence until time t minus 1. Now, if I again maximize it over this j, then I will be accounting for the most likely state sequence until time t, and that's my S star. So this j, which has the most or the highest value of delta tj, is in fact the last entry of the string S star, which is what we are, and S star is what we are eventually looking for. So this is what we do next. After running the main algorithm, S star t equals argmax I delta ti. We don't need the probability of the string. We need the string itself, and here we extract the last end of the string, S star. So this S star t is the most probable previous state at time t. What about earlier states, t minus 1 until 1? Not actually, this is not previous state, it's most probable current state at time t, because t is the current time. And what about the earlier states? T minus 1 through 1. So for that, we have to backtrack. From this expression here, rho t plus 1j tells you the most likely previous state. When you're in time step t plus 1, what was the most likely previous state at time t? And this is shown here. So at time step t plus 1, the HMM is in state j, and rho of this state here at t plus 1 would give S star, that's S star t plus 1. And rho of S star t plus 1 would give us S star t. So that's the most likely state at time t, s star t. So that's how you go backward. From s star t plus 1, if you take the row, you get s star t, and then from s star t, if you take the row of this, you'll get s star t minus 1, and you backtrack like that. So this is the backtracking portion of the Viterbi algorithm. For t equals t minus 1 to 1, once backtracking, s star t is row of t plus 1, s star t plus 1. And this is the complete Viterbi algorithm. Now what's the time complexity? So let's look at the main loop, the recursion. The outer for loop runs t times, actually t minus 1 times, but we are looking at order. And the inner for loop runs for n times, n is the number of states. And the argmax and the max are being carried out over states. So they're both order n, and therefore the complexity of Viterbi algorithm is order n squared t. The end.